This is fundamental problem 1510. In this problem, the spring is fixed to block A, and block B is pressed against the spring. If the spring is compressed by 200 millimeters, and then the blocks are released, determine their velocity at the instant that block B loses contact with the spring. The masses of blocks A and B are 10 kilograms and 15 kilograms respectively. So in this problem, we are going to use two conservation laws. We have the conservation of impulse momentum and the work energy conservation law. The system will be block A and block B acting on the system in the horizontal direction. We have no external forces. So using our impulse momentum conservation law, the impulse is equal to 0. We have two objects in our system. We have object A and object B, so we can do the sum of the momentum for object A and B plus the impulse of 0 is equal to the sum of the final momentum for object A and object B. That gives us the mass of A times the velocity of A initially plus the mass of B times the velocity of B initially with an impulse of 0 is equal to mass A times velocity of A finally plus mass B times velocity B finally. And also we can use the conservation of energy, and I think we are supposed to assume in this problem that the surface is smooth, and so we only have the normal force acting upwards, the force of gravity acting downwards. The normal force is not doing any work since the blocks are moving perpendicularly to the normal force. Instead of using the force of gravity, we would do the gravitational potential energy, but since the surface is level, the change in gravitational potential energy is 0. So from our work energy conservation law, we have kinetic energy plus elastic potential energy plus the work done by non-conservative forces, which is 0, is equal to the final kinetic energy plus the final elastic potential energy. So we have, let's say, initial kinetic energy plus initial elastic potential energy is equal to final kinetic energy plus final elastic potential energy. For the kinetic energy, we have to look at block A and also block B. And we are told the blocks are released starting from rest, so the kinetic energy for both blocks initially is 0. We have a spring constant given to us of 5 kilonewtons per meter. The spring is initially compressed by 200 meters. For elastic potential energy, we have 1/2 kS squared. So the initial energy that we have is just the elastic potential energy. And the final kinetic energy is the kinetic energy for block A plus the kinetic energy for block B. The two blocks are not moving together afterwards, so we have to do the kinetic energy for each one individually, plus the final elastic potential energy. But if we are looking for when block B loses contact with the spring would be unstretched at this point. So the final elastic potential energy is 0. Now we have two equations and two unknowns. This is equation 1. This is equation 2. We know mass A, we know mass B, and the initial velocity is 0 for both A and B. So we only have two unknowns in these equations. We are looking for the final velocity of A and the final velocity of B. So we can put in everything that we have and solve our two equations and two unknowns. So let's take equation 1 and solve it for VA2. So we have VA2 is equal to MBVB2 over MA. Then we can take this and we can put it in equation 2, and we have 1/2 KS1 squared is equal to 1/2. If we put this in here, with MBVB2 over MA squared plus 1/2 MB times VB2 squared. And let's simplify this a little bit more before we put some numbers in. So this is 1/2 KS1 squared, 1/2 MA over MA squared would leave us with an MA in the numerator and an MB squared, or an MA in the denominator and an MB squared in the numerator. Then we have a VB2 squared here plus 1/2 MB VB2 squared, and the right hand side can be written as 1/2 and we can solve this for VB2. That is the square root of the 1/2 on this side cancels with the 1/2 on that side, so we have a KS1 squared divided by MB2 squared over MA plus MB. And you get to put the numbers in on your own for this. You should get 2.31 meters per second. Then when you have VB2, you can go back to the expression that we have here and solve for VA2, and you should find that VA2 is equal to 3.46. And if you want to see what we have when we plug the numbers in, this is the work with the numbers. And that is it for fundamental problem 10.